and then we overcome that painful period. And now to synthesis indigo. So you all know how important indigo is. So that was the only blue color available during that historical period. And uh, I am sharing my screen. Yes. So today we will synthesize indigo from acetone and 2-nitrobenzaldehyde. So we will use acetone and 2-nitrobenzaldehyde to synthesize indigo. And now I request Shumon to take care of this uh, synthesis part. What exactly happening when acetone is reacting with 2-nitrobenzaldehyde, and discuss about this. So
Yeah.
shall I stop sharing?
Maybe I can override. Let me try. Yeah.
So
Okay.
it okay.
Should be my screen should be visible.
Uh,
Mm,
I cannot see your screen.
is it?
Yes, because I am
We can
present.
see the screen, sir.
So you can stop maybe. Yeah.
Yes. So I'll share it later again when it is required.
Okay. Is the board is visible to you guys?
Yes, yes.
Yes, sir.
Okay, perfect. I'm just trying to change the background color. Maybe blue is better. Yellow. Okay, let me try this. I haven't tried it before. Yeah. So you can see the drawing.
Yes, yes.
Okay, perfect. So I apologize. Maybe the structure will not be as good as the board. So I'm trying it for the first time. Need some practice. But anyway, as Professor Haldar mentioned, so of course it was the discovery of this indigo was a big thing worldwide, especially for India. It was having an added advantage, and especially for Bengal, as Professor Haldar said, the British people really forced the poor farmers of Bengal to cultivate indigo rather than cultivating rice or wheat. Okay, so that's why it was really paining period. But this discovery of indigo, but by Bayer, Professor Bayer, and then later on he formed this company Bayer. It becomes much more cheaper compared to the agriculturally produced indigo. So then, of course, the all business of British by extracting from the natural source got shut down, and people started synthesizing indigo chemically. And the reaction they used, Professor Bayer used, was a pretty simple one. Basically, it was a consecutive aldol type reaction, and the starting material used for this one is basically this orthonitrophenyldehyde and damn cheap acetone. Acetone, as you know, it's people use as a solvent, even for washing. People use it. It's very very cheap. The acetone, and this orthonitrophenyldehyde is also quite cheap. Normally, this orthonitrophenyldehyde are produced from orthonitrotoluene. Just by simple oxidation of orthonitrotoluene, you can get this orthonitrophenyldehyde. But in our case, in our practical, so this is commercially available. So we'll use directly this orthonitrophenyldehyde and react with acetone. And in this reaction, as I said, it's an aldol reaction. And as you know, in aldol, you need something, a catalyst, either a base or acid. And base catalyzed aldol are more popular or more common. In this case also, we need a base, and there also it's a cheap base like sodium hydroxide was used. And now, so whenever you mix a base and acetone, you know, it's a active methylene group is there, some acidic proton is there next to ketone. So acetone, if you mixed acetone with the base, that's a OH minus, so definitely you will form the enolate. And once you have the enolate in medium, it's a nucleophile, the enolate, and as you know, this is a electrophile, the benzaldehyde. So immediately these two guys will react, and you form the first intermediate. So although this reaction is bit, it's very easy, just mix and thing. You will see in the video how easy it is. Just by mixing, you will get immediately the product. But the reaction mechanism is a little bit tricky. I will make it as simple as possible. So this is the first intermediate that we get. I'm just expanding the nitro here so that it will be easy afterwards. But you still have base in the medium, right? So we'll use plenty amount of base. So bases are roaming around, and it will grab proton from here and from further enolates. It's like this, form another enolate here. Okay. Now you see, of course, this enolate ideally can react with another aldehyde, but if for any nucleophile, if something is available, some electrophilic center is available intramolecularly, so then intramolecular reactions are always facile, because you can see intermolecular means your two molecules really need to come too close to each other and need a collision. And intramolecular means it's just available, the reactive center is available in close proximity. So then intramolecular reactions are always facile. So rather this guy reacting with another aldehyde, it will prefer to react here. Okay. In each cases, this will take a proton whenever we are pushing. Sometimes I skip this part. Suppose here you see because sodium hydroxide is there means some water is also there. So whenever some proton is required, it will take a proton and becoming OH here. You see. So I'm skipping that part because you are now third year students. So this much skipping should not be a problem. So giving a proton and taking proton is quite common in organic mechanisms. Okay, so we are here now. So you see, just by doing this one, so this is the nucleophilic center. We are forming 1, 2, 3, 4, 5-member ring here. So that is what we need. This 5-member ring here, and we have a OH here, O minus here. Look at the charge here, because we are pushing 2 electrons here on nitrogen, and 2 electrons is going away from nitrogen. So the charge, formal charge on nitrogen remains as it is. Okay, so it should be plus, and this part is becoming ketone. Okay, this is the situation here. As I said, we'll use plenty of base. So here we have one OH is here, no? Here HCH was there. We are grabbing one. So here is still one. So that's this is the guy. I'm showing it now because we need it now. Here like this, its base will grab this guy. This will come here, and this will leave as water. So we are here now. Standard steps, just you need to know the sequence, nothing that complicated. Okay, so we get a double bond here. is still minus and plus, and OH here. Okay, so this guy was having a H. Now we need it. That's why I'm showing it. So basically, it's a tautomerization, or you can say release of proton. Better to say. So it's just because nitrogen is positive. Now there is the opportunity that nitrogen becomes neutral. That's why it is going there, and this proton is grabbing by this minus. So we are here now. Nitrogen becomes neutral. This O minus also becomes neutral. Here, this becomes OH, and this is as it is, whatever was there. Okay. So now this, you see, this is a enol ether now. Sorry, enol here now, not ether, enol. So enols are not that stable. So rather, it preferred to stay as other tautomer, that is the keto form. So it will just tautomerize. Better to how to take the eraser here. Better to give a reversible sign rather than giving like this. This side is more facile. That's a bigger arrow here. We are almost there. OH. Okay, so this is the situation. Now, there's something interesting will happen. This here, OH minus. I'm skipping one step actually. This way ideally will go up there, O minus. I'm skipping one step. That's why I'm showing that this O minus will go and then come back. And this guy will keep this carbon-carbon bond and release one water. So basically, it's like this. Basically, it's a decarboxylation reaction here. Oh, this carbon-carbon bond is getting clipped, and not decarboxylation. This is basically forming acetic acid. Okay, this part just going there, O minus, and coming back and cleaving this bond, and then releasing water. So what you get here, you see, I get this nice 5-membered ring here. Take okay, this guy here. This is the situation here. Okay, this guy, this intermediate, this will serve as our electrophile. You will see later on. We need this guy. Okay, so electrophile for the coupling. This guy. But once we, if you see the structure of indigo, so that is basically two things attached together. You will see in a minute. It's basically at the end there is a dimerization or two molecules reacting with each other. That is also one nucleophilic and electrophilic reaction coupling. Okay. So in electrophilic and electrophilic, we need one electrophile. This will serve as our electrophile. You will see now our nucleophile. I need some space. I'm erasing this part. I don't know whether I can select and just maybe I also need to practice with the Jamboard. This much space will be good enough for us. Okay. Okay. So the thing is, so we will generate during the reaction. We generate a lot of species of this molecule. This electrophile will generate in a large quantity. But what will happen? Some of these electrophiles will, you see, it will have some will get modified. Okay, so some will remain as it is, and some portion will be modified like this. So this is the thing we drawn. This is the same molecule, this guy, electrophile. What will happen? We have plenty of OH minus, this will be there. And H, OH, okay? And still have one H here. This will get tautomerized. Of course, here, the same thing, reversible. OH, OH, okay, NH. Now this is ready. Our nucleophile is now ready. So this guy will serve as nucleophile. This is the nucleophile. Just the simple modification of this electrophile here by adding this OH minus and simple tautomerization will get this species. This will serve as nucleophile in our case. So once we have both the species in the medium, nucleophile and electrophile, then what will happen? It will couple to with each other. See now. Let me create more space. Although I'm telling this, I don't know how long I have spoke already, maybe 10 minutes, but you will see in the video, once we mix, immediately it will happen within a minute, or within not even minute, within few seconds, because these reactions are very, very fast. Yeah. Okay, I think that's good enough. This space, let me go back to yellow color. Okay, so our nucleophile is there, electrophile. Let me first draw the electrophile again. Here, what I'll do, I will draw it upside down, the other guy. Then it will be easier. It's the same thing. The same nucleophile I'm drawing just by rotating. Okay. It's not a chiral molecule, don't have to think of before rotating, so it should be fine. Yeah, the same thing here. Just by rotating upside down, I missed one double bond. Yeah. Now what will happen? So this will push electron and this will add here. That dimerization happens. What we'll get? We are almost there. H. This carbon-carbon single bond. There we go. The OH is still there. This becomes CO. Okay. Last step. This is the last step. This will go and water will get released. And finally, we'll get our desired indigo. Just a moment. The last structure is coming out with some space here. Let me draw it properly. On HCO. So this is going there. So this is becoming carbon-carbon double bond. And here you go. Like this. Yeah. Okay. So this is the final molecule, the indigo. And why is colored? You can see the conjugation. You see, this nitrogen will donate lone pair, and then this will go flow all the way to here, and same here. If you keep electron there, it can flow all the way to this ring. All are conjugated. There is no So all the carbons here are sp2 hybridized, right? So all the carbons, so all are having some multiple bonds, and this nitrogen having some lone pair of non-bonding electrons, so that can also get involved in conjugation. That's why this molecule is highly conjugated. Okay? And it's absorb light in visible region, and the rest, whatever not absorbed, is the blue portion. So that's why we see a beautiful blue color, or after it's called as the indigo color, basically. uh, for it's already known as indigo color, that particular color. Okay, so this is the mechanism, although it's a bit lengthy, but this just no complicated steps, simple protonation, deprotonation, and carbon-carbon bond formation, like aldol type reactions. But you may need to know the sequence, you need some practice, so that you can remember the thing. Okay, so that's all for the mechanism part. You can also, if you just type in Google, you will get the mechanism, even probably from in the Wikipedia or in organic chemistry portal is there. They will get the mechanism, or you can see from the video that I will upload in the YouTube, or will and link is there already. You can see the mechanism sequence as well. Okay, so I will now go back. Oops, what's happening? My mouse is.
So, Shumon,
Yeah.
yeah, so may I show that what they have to do the experiment, and then
Yeah,
you can
sure.
go
Please.
back to that video. Yeah.
Yeah. Let me stop sharing. Yeah, that's it.
Yes. So what you have to do exactly in the lab, just you need to take 0.5 gram of orthonitrophenyldehyde in a conical flask and dissolve it in 5 ml acetone. So again, it's roughly, you do not need to be very accurate. So just use a glass rod. If the dissolve there is any difficulty in dissolving the orthonitrophenyldehyde in acetone, just scratch it and it will dissolve. So once it's completely dissolved in acetone, add 5 ml of water with constant shaking. So you will get the reaction mixture, and with that just add 2.5 ml of 1.0 normal NaOH solution. So the NaOH solution will be supplied. You do not need to prepare it. If it is not supplied, just dissolve one bead of NaOH in 2.5 ml water, and then dropwise add that NaOH solution to that reaction mixture with continuous stirring with a glass rod, and immediately you will see a blue color is appearing, a color change, the color of indigo is appearing, and the reaction vessel, that is the conical flask or the beaker, it will be little bit hot, and you will see that the reaction mixture is under it looks like a boiling condition. So because in the reaction, this is exothermic reaction and acetone is there, so it will looks like a boiling condition. Just to wait, nothing to be worried, wait for 5 minutes, and then you will get the precipitate of indigo, and then filter that indigo precipitate through that centered funnel using aspirator, and wash that indigo with cold water and cold ethanol, and then you can check that characterize your compound by UV visual spectroscopy and 1H NMR, proton NMR. So I will share that proton NMR and UV visual spectroscopy in WeLearn. And so you can write the peak position for 1H NMR and UV visual spectroscopy, and the peak responsible for, and also for 1H NMR you can analyze the data. So you can take help from the TS if you have any doubt. Okay, so that's it. I just stop sharing. Yeah. So Shumon.
Okay. Let me share the video. Hopefully today you can hear the sound also.
So welcome, Yes, it's CH3204, fine.
Experiment
experiment number 2.
Perfect.
So today we are going to synthesis indigo from orthonitrophenyldehyde. So orthonitrophenyldehyde and acetone will undergo condensation reaction in presence of sodium hydroxide and make indigo. So for that reaction, the reagents we need are ethanol as a solvent, and then sodium hydroxide, orthonitrophenyldehyde, acetone. So we will do the reaction inside 100 ml conical flask. So first we will take acetone 5 ml in the conical flask. So we have already weighed 2-nitrobenzaldehyde, orthonitrophenyldehyde, 0.5 gram, and we have taken inside the conical flask. Now we are adding acetone 5 ml to this solution, to this orthonitrophenyldehyde. So by stirring, we'll dissolve the complete orthonitrophenyldehyde in acetone. Yes, so it's dissolved completely. And now we'll add 5 ml water to this solution.
Because you see, we have done a lot of protonation, deprotonation. This water, I've mentioned at that time, this O minus is taking proton from water. In many cases, nitrogen also. Yeah.
Next is by stirring. So we have added 5 ml water in solution of orthonitro and the
Yes. Better to add slowly because water is yeah.
reaction at room temperature.
Yeah. So what I'm saying that you need to add slowly the water because orthonitrophenyldehyde, it's an organic compound and water is not an organic solvent. Acetone is an organic solvent, so that's why orthonitrophenyldehyde perfectly soluble in acetone, but it's not that good soluble in water. But when we are adding water into acetone solution, so then we have it's a mixed solvent. So it's also good enough. But if you add water too fast together, so what will happen in some portion, the concentration of water, the ratio of water will be too high compared to acetone, right? So in that part, whatever benzaldehyde is there, orthonitro, may precipitate out. Okay. So we don't want that. We want the orthonitrophenyldehyde to be in the solution in the insoluble state. That's why if you add slowly, so then the ratio of water and acetone will remain in ideal condition, and then you will not get the precipitate. But if you add fast means you may get some precipitate. That's why photosecant is adding slowly and with stirring just to keep the ratio ideal.
And now we will add sodium hydroxide on normal solution. So we have sodium hydroxide pellet. So we have dissolved sodium hydroxide pellet to prepare 1 normal sodium hydroxide solution. So we are adding 2.5 ml.
Oh, you see, yeah. You see already the color appearing.
And indigo uh, prepare.
Let me rewind and then you see.
1 normal.
Yes.
So we have sodium hydroxide pellet. So we have dissolved sodium hydroxide pellet.
By this time he's adding, already added. So all the intermediates are forming. Now his color is changing. You see, yeah. Changing already. Yeah. Okay, perfect. Becoming blue.
Immediately the reaction start and indigo uh, appeared, and so you see the color of the solution turn dark blue.
Within 10 seconds probably.
So this is a condensation reaction, very fast reaction. Already you can see the indigo is precipitating out of the solution.
Yeah, it's so concentrated. It's appearing to be black, right?
Study for 5 minutes, and then we will go for filtration to collect the indigo.
Yeah, but if you have a dilute solution, then you'll see it's blue.
5 minutes we are filtering off the indigo. So first we prepare the Bugner funnel for filtering. So this is the aspirator, and there is a pump inside. So this is the Bugner funnel. On top of Bugner funnel, we have set up the filter paper, and now we are adding our reaction mixture on the Bugner funnel. So the indigo is collecting on the filter paper. So we will wash this with cold water.
It's so concentrated, that's why looking like a bit blackish. But as I said, diluted thing will be nicely blue indigo color. It's always a good practice to wash your reaction vessel properly so that you can minimize the loss of yield.
So that is the indigo. You can see the nice blue color. So next we will dry this indigo as much as possible, and then we will use this indigo to characterize with FTIR and NMR spectroscopy, and obviously we will do an UV visible spectroscopy because this is a color compound.
All right. Yeah.
Shumon, thank you very much. So now I will show you the UV visible and NMR spectra of the indigo. So I will share that with you. Mm, yeah. Yes, so that is the UV visible spectra of indigo. The peaks are already written there. So you can see the peak. So only what you have to write in your notebook, the which peak is responsible for which transition or why the peaks are appearing. And so going through many spectroscopy courses, so you already know that there are which kind of transition n to pi star or pi to pi star or whatever it is. So that you have to write. This that's it. And this is the NMR spectra of that indigo. So here it's already mentioned the peak position. So just you have to write this analysis in your notebook.
One comment there is the so
Yes.
previous slide. Um, it's appears to be one derivative of indigo. This SO3Na.
Ah,
People use
yes,
this,
yes,
yeah.
yes.
People use this to make improve the solubility of indigo in water. Right.
Mhm. Yes,
So
yes,
this
yes.
is just an error in the structure, or is a spectra of this?
No, so the spectra will not change much. So the spectra will
Yes,
not
that's
change.
true. True.
Yes.
True. Yeah, okay.
Mm.
Yeah.
So
The major
generally we
major
use.
core is the same. Yes.
Yeah, yeah, mirror code is the same. Generally, we use indigo for coloring our dhoti or sari, which is white
Yeah.
in color,
Jeans
and
as well.
that's
Yeah.
why we need to dissolve that indigo quickly in
In the
water.
water. Yeah, that's
That
true.
functionalization was to make it quickly soluble in
Follow in
water.
water. In this particular case, you see this precipitated out from water and very dark color. We washed even with water, not that much soluble in water. But if we have this SO3 and SO2Na, it'll be much more soluble. Yes, true. Okay, yeah.
Yeah. And so this is the NMR. So you can write the analysis of the spectra or where the protons appear. And yes, that's it. Yes. So any question? Yes, the
Any,
students. Any
yeah,
question?
any doubt, guys? By the way, Somojit, you are here, right? There's IP, the only
Yes, sir.
IP. Okay, okay, perfect. So appears to be, as they were muted, yeah, appears to be no question. Is things are clear. Okay, sir, it would be great if TS share the numbers. Which numbers? Oh, the mobile number, you mean? Mm-hmm. TS email ID will get there in the VLAN itself from the participant list, I guess. Participant list is also visible to you, right? All the participant list. Mobile number, okay. You please ask them by email. I also don't have mobile number of everyone. You can send email. Not really. You can't say umpulang. Umpulang is a reversal of polarity. We are not doing that here. So, like, if you consider the first reaction, the benzaldehyde, which is acting as electrophile, so it's normal. If you can somehow change the polarity of the carbon present in benzaldehyde, that aldehyde carbon, then it's called umpulang. But in this case, it's not happening. So it's a normal reactivity, not umpulang. How is self-aldol condensation prevented? Yeah, that's a good question. Yeah, basically acetone is there. So acetone may condense with each other. So maybe little part will happen. But you see, once you form the enolate, if you recall the mechanism, let me share the screen. That will be easier for me to. Oh, I have erased that part. Sorry. So let me just say by just by voice. So you remember we generated the enolate from acetone, right? So there is two possibilities that acetone, that enolate can react with another molecule of acetone, or it attack the benzaldehyde. But now if you compare the electrophilicity of benzyl aldehyde and ketone, so aldehyde are always more electrophilic compared to ketone. Ketone is always having two alkyl groups, right? So, and alkyl groups are normally electron donating with plus I effect. So that's why, and also it's more sterically crowded compared to aldehyde, because aldehyde means there is always one hydrogen there. CHO, H is there. It's sterically less crowded, and the electrophilicity also high. Yeah. And in this particular, this is the general trend, and in this particular case is because of the presence of the nitro group. Nitro group is ortho to aldehyde, so this aldehyde becomes super reactive, is very electrophilic. Okay, so once you form the enolate from acetone, immediately it will react with that aldehyde. And now comes to this aldehyde part. So if you say acetaldehyde or any other aldehyde which can form enolate itself, then it can self-condense. But in this particular case, because it's a benzaldehyde, right? Benzaldehyde derivative, there is no alpha proton. Okay, so self-condensation of aldehyde is already not possible, and self-condensation of acetone is possible, but it's very not less favorable compared to reaction with acetone and aldehyde. Okay, so that's why self condensation is very much minimized. Yes. Okay. Any other doubt, query?
So if you do not have query, so we will upload that PowerPoint file in WLAN, and the
Also,
video will,
video. Yeah, everything, all the videos. Two couple of both the experiment video and the lecture video.
yeah.
I will upload in YouTube like last time.
And so you just submit your notebook, whether it is a PDF file or JPEG file. So before the next experiment.
Yeah, so I have seen most of you say at PDF, so that's good. Yeah, PDF is better.
Yeah.
Okay, guys, then we finished within an hour today. That's good. So you can have good lunch. So you'll not stand between you and the lunch. Goodbye and have a nice weekend. So we are closing it here. Yours is the then?
Yes, yes, yes.
Okay,
Thank you so much. Okay.
okay.